Welcome guys. So this video, let's talk about Ramsey theorem. Okay, so Ramsey theorem is a very interesting theorem that yes, better than this animation. Okay, so Ramsey theorem basically has many different versions, but in this video we prove this very simple version called a monochromatic triangle. Okay, so this is also not very easy to pronounce. Okay, so Ramsey theorem says that for r greater than 0, then n will be function of r. So n is another integer, a positive integer. If the edges of the complete graph kn is colored using r colors, so you have a complete graph. So that basically you have n vertices, and for any of two vertices, there's a edge connect them, and then you color all of these edges using r colors. Okay, and there must be some monochromatic triangle. So basically, monochromatic triangle, that means that there is a triangle and all of its edge has the same color. All three of edges. So the application in the previous video, you can go to my video channel and type the additive combinatorics, or basically you just type the famous theorem on friends and stranger, you can see the proof. Okay, so this is very famous that if you collect six people in the room, and 3 of them will be friends, and 3 will have, or there are two cases. One is 3 of them be friends, one of these 3 of them must be stranger. This theorem is so amazing that yeah, so I never found this is true until I go to college. Okay, the proof is that if you try to draw a complete graph for 6 vertices, then somehow like that you will find that you cannot avoid the monochromatic triangle. So you always find some monochromatic triangle. And the theorem basically fails for n equals to 5. If you only have 5 points, then you can create like star shape. So you see, this star shape do not have the monochromatic triangle. There is no red triangle, and there is no blue triangle. But basically, the Ramsey theorem tell you that when r equals to 6, when r equals to 2, n equals to 6, then you meet the bound. So this example just the r equals to 2 Ramsey theorem case. Okay. So Ramsey theorem tells you that this n must exist. Okay. So now see the proof. Okay, so the proof is very easy. Okay, so hopefully for you it's easy. Okay. So let's do the induction for R. This is very easy. So suppose you only have one color, right? You only have one color, and then what else you can do, right? You take 3 points, and which is complete graph. So there is a triangle, right? This monochromatic triangle that all of it is red. Let's say I use red as color. So when r greater or equal to 2, that's suppose the claim holds for r minus 1 color. So basically, I know there's n, right? Basically, it's n r minus 1. I call it n. So basically, every complete graph with the more than n vertices must have some monochromatic triangle in this graph. Okay, I define n prime to be n r minus 1 plus 2, and I claim n prime works. So I claim that n prime. I claim that if you use r colors, then in n prime there must be some monochromatic triangle. Okay. So proof is that let's focus on this point, right, and connect all these points. So for this point there will be outgoing edge, which is n times r minus 1 plus 2 edges, and then you use r color, right? You use r color. So by the pinch principle, there at least has n edges. So if you divide by r and take the ceiling, then you see there exists n edges. So there exists n edges which has the same color. So let's say this color is green. Okay, I mean I just choose green. Okay. Okay, so let's call all of these. Let's call all of these vertices, all of these n points, all of these n vertices, and all its connected edges called V0. Okay. So there are two cases. So if V0 has a green edges, so remember, if green knot has any green edges, then there will be monochromatic green triangle, right? So there is a green monochromatic triangle. This is the first case. Okay, so the second case is that if V naught does not have any green edges, then we also know that V naught has r minus 1 color, right? Because because we use r color and then there is no green here, so we have r minus 1 colors. Okay, so V naught has a monochromatic triangle, right? By our induction. Okay, so there's always a monochromatic triangle here. Okay, so this proves the Ramsey theorem. I want to talk about how to use the Ramsey theorem to prove this Schur theorem. Okay, so this Schur theorem is very, very amazing. I mean, this is the amazing math theorem that I mean, when I first time saw it, I think, oh my God, it's very mind-blowing theorem. Okay, so this theorem is very interesting. So I want to give you guys some examples before we go into proof. So just to want to make sure that you feel it's also amazing. So theorem says that there are two versions. Okay, so maybe the infinite version is basically it's easier to understand. So if n is finitely colored, okay, so what it means is that if you try to just color integer for finite color, so let's assume that we prepare some color, which is red or blue or basically any finite color, and then you assign for each integer. Let's say you can color the number 1 to be red, and the number 2 to be blue, and the number 3 to be yellow. And so you try to cover all the integer by some color. Then there exists some monochromatic solution, such that x plus y equals z. So that means you can always find x and y and z belongs to integer, positive integer, such that they are all the same color, and z is equals to x plus y. Okay, so this is the proof. This is the theory. Okay, so let's talk about the finite version. So the finite version is the same as means that for r greater than for r which is a positive integer, then there exists some number, and then if you denote this the set of 1 to 2 to n as this set bracket n, there exists a monochromatic solution to x plus y plus equals z. Okay, so this is like the finite version. Okay. So before we start, let's maybe talk some example to that you feel this theorem is so mind-blowing. Okay, so let's assume that we only use two color. So let's assume that we use only like say red and blue. Okay, and then we color like 1 to 2 to n, and then we try to avoid a situation that the x, y, and z are has the same color. Okay, I should say have the same color. Okay, and such that x plus y equals z. Okay, so let's see an example. So let's suppose I color 1 to be blue. Okay, then I cannot color red to be blue, right? Because if I color red to be blue, then 1 is blue, and 2 is blue. So 1 plus 1 equals 2. So I cannot color. I must color 2 to be red. Okay, now I go to number 3, right? And so 3 is equals to 1 plus 1, 1 plus 2. So there's no condition for 3, right? But so let's assume that I color 3 to be blue, right? And how about 4, right? So 4 cannot be red, right? Since 2 plus 2 is 4. So if 4 color to be red, then 2 plus 2 will be 4, right? But as you know that the 4 cannot color by blue, right? Because otherwise that 1 plus 3 is 4, right? So no color is suitable for 4. Okay, so this is, so now you see the theorem works, right? You always find a monochromatic solution, right? No matter how many color you use. Okay, so let's go back to the another case and try to see whether we can avoid this solution. Let's review now. So let's color 1 and 2. So 3 must be color red, right? So now let's assume 3 must color, and 4. So 2 plus 2 is 4, right? So 4 must be color blue. And let's say, and now 3 plus 3 must be blue. So 6, right? And but you see 2 plus 3 is 5. So 5 comma beneath, right? But then what is the there's a contradiction here, as we mentioned. Where is contradiction? So yeah, 6 and 6, right? So and you see 6 is 1 plus 5, right? So this must be. So there's a contradiction, right? So you see, if you only use 2 colors, then up to 6, then you already fails. Right? You cannot avoid the monochromatic solutions. Okay, so basically the idea for this theorem is that no matter how many colors you use, you always cannot avoid all the monochromatic solution. There's always a monochromatic solution such that x and y and z has the same color and x plus y equals z. Okay, okay, so in this let's just prove the finite version and the infinite form. Okay, so the first we just proved that the finite form and the infinite form are the same. Okay, so the first one is that the finite form must implies the infinite form, right? This is obviously because up to n, then you already fail. Okay, so infinite form will imply finite form. The reason is that suppose not, then for some, let's say for some r color, right, and you have all, and for some r there, for all integer, then there exists the phi n, right, mapped to the 1 to n to 1 to r, such that phi n avoids all the monochromatic solution to x plus 1 equals z. Then basically you can take the infinite subsequence of this phi n k, such that phi n k will stabilize as k increase. So basically you pick up some subsequence, okay, and for such subsequence it will stabilize. So phi n k converted to pointwise to color such that phi will cover all the integers that are avoid x plus y equals z, and but this will contradict to infinite form. Okay, so the amazing result is that actually you can use the first theorem called Ramsey Theorem for the monochromatic triangle, and then get your Schur Theorem. Okay, so remember the monochromatic Ramsey Theorem says that you have a complete graph, and if the vertex is large enough, then there will be a monochromatic triangle. Okay, so now we need to connect this monochromatic triangle to the monochromatic solutions. Okay, so to connect is let's suppose, okay, so for r greater than 0, so I want to first create a complete graph. Okay, so let's assume phi map to n to r. So this is just color n vertices. So now in origin, let's suppose we have n points, right? 1 to n, and we color from r. And so let's build a complete graph. So I build a complete graph for each. So this complete graph is has the same n vertices, right? But for each color, the color I define to be j minus I. So the color of edges will be phi j minus I. So basically, I create a complete graph, and each vertex is labeled by I, j, k. Okay, from 1 to n, and for the edges connected I and j, the color will be phi of j minus I. Also, color of each edges is phi j minus I. So let's assume that you have I and j and k, and so the color from these edges is phi j minus I, the color from these edges is phi k minus j, the color from these edges is phi k minus I. Okay, but from Ramsey theorem, we know that this is complete graph with n, right? With n vertices, so there exists the n such that the monochromatic triangle. So that means such exists ijk such that the phi j minus I, phi k minus j, phi k minus I has the same color. Okay, but if you're smart enough, right, you just let the j minus I to be k minus j to be y, and j minus I to be x, and k minus I to be z, right? And then you see that let's say x plus y equals z. Okay, so j cancel. It's x plus. Okay, so that means it's very mind-blowing that the Ramsey theorem basically is a theorem in the graph theory, right? But in the graph theory, you can transform the graph theory theorem to prove this amazing number theory called Schur Theorem. Yeah, so this is the very mind-blowing results, or very mind-blowing consequence about how to connect the graph, how to connect somehow people call extremal graph theory to the theorem in the number theory. So this Schur theorem also very mind-blowing that somehow it's, I mean, intuitively you will think it definitely is correct, right? But it's not so direct to see why Ramsey theorem will imply Schur theorem. Okay, that's it, and I will see you guys in next videos.